All right, folks, welcome back. So in this video, we'll look at complex integrals that are defined in the complex variables. So a complex numbers are associated with vectors, right? We can express complex numbers as a vector. So with vectors, and most of the integrals that deal with complex variables are going to be line integrals, okay? So let's look further about contours in the complex plane. So what is a position vector? So a position vector, let's say this is a curve in the complex plane, okay? So this is my complex plane C, the real and imaginary components. And these are my starting point. So A is my starting point, and then B is my ending point. So we can figure out where this particle is moving along this curve by associating a position vector. So we'll call this point Z of t. Okay. And so Z of t is a coordinates x and y, but they are associated with a time variable, right? So so Z of t, this is what's called the parameterization. The parameterization of the curve, right? And so we can associate values on this curve with like Z of t1. This could be like Z of t2, and so on, right? T, the parameter t, is in between A and B, right? A and B are different time values, right? And so Z of t, which is defined as x of t plus I y of t. This is what's called the position vector. There's also the derivative of this guy, right? This is what's called the tangent vector. Okay. So this is what's called the tangent vector. And this would be a vector that will look at the rate of change in vectors Z of t and let's say Z of t plus h. So what we want to do, so how this tangent vector is formulated is we want to look at the vector that is going in the direction starting at, oops, let me undo this. Darn it. Oops. So we want to calculate the vector that is going from Z of t to Z of t plus h. And then we just let h go to 0. And if h goes to 0, that will indicate Z prime of t. All right. So that's what's called the tangent vector. And there's a couple of important things to know. There's going to be, so when we parameterize curves, we're going to have what's called the positive orientation of the curve. So what is the positive orientation? So these are values acquired when t increases. Okay. All right, so for example of a circle, so for just say an example, the parameterization of the unit circle, e to the it, where t is in between 0 and 2 pi, right? So when t increases, our circle of radius 1 starts at 1, 0, and then it goes to 0, 1, that's pi over 2, and then minus 1, 0, minus, I'm sorry, at pi, and then 0 minus 1 at 3 pi over 2. So when t increases, the positive orientation would be counterclockwise. So we're going to go this way. So that's what's, so the positive orientation is counterclockwise. For a circle. Okay? So that's what's called positive orientation. It's the way that the curve is traveling when t is increasing. Okay? There's also negative orientation. And it's exactly the opposite of the positive orientation. So this is a curve that is traveling in the opposite direction. So in the case for a circle, for example, is clockwise. Okay, so it's clockwise rotation. Okay, so that's a little bit of review on contours. And so let's get right into what a complex integral is. So we can define a complex function in terms of the real component, which is a function of u, of x and y, plus I times a imaginary function v. Okay. And okay, so all right. And we can also define dz as the derivative in x plus I times the derivative in y, right? The change in x and the change in the y variables. Okay. So then f of z times dz, well, this equals to ux y plus I times v of xy times dx plus I times dy. Okay. And this would equal to, so, okay, so in terms of the real components, we'll have u of xy dx, and this is minus v times x times y dy. And then the imaginary components would be plus I times v of xy dx, and then plus u times xy dy. Okay, so that is what f of z dz means. Okay, but since we're going to deal with line integrals, the z is a function in t. So z is expressed as x of t plus y, I times y of t, right? Where t is in between a and b. So z of t is a parameterization, okay? So, and this would equal to, so this would equal to, so so I guess the line integral, it's not closed, we don't know that. So the line integral of this quantity dx minus v times xy dy plus I times the line integral of vxy dx plus u of xy dy. Well, this equals to, in terms of t, this is equal to u of x of t, y of t, times x prime of t dt, times x prime of t. Let's say that, minus v of xt times y of t times y prime of t dt plus I times ab times x prime of t dt. And then plus u of x of t, y of t times y prime of t dt. Okay. Let me erase that and put this in parentheses. Okay. Good. So this big quantity right here, this is just another way to express the integral of a to b of f of z of t times z prime of t dt. Okay. And this is how we would define a complex line integral of z dz. Okay. So a complex integral is a complex line integral is the following. So the complex line integral of f of z dz is equal to the integral from a to b of f of z of t times z prime of t dt. Okay. So part of the work is we want to parameterize z in terms of t. Okay. So that's going to be part of the work. So I'll show you an example on how we would do this. So find, so this is the line integral of the closed curve of 1 over z dz, where C is a circle of radius 2. Okay. And then t is in between 0 and 2 pi. Okay. So part of this work is we need to recall how to parameterize lines and then circles and line segments, right? Those type of curves that we've seen in previous chapters. So in this case, we want to parameterize a circle. Okay. So we need to recall some curves to parameterize a line, right? R of t, I'll just call R of t. This equals to 1 minus t times z 0 plus z1 times t, right? A line segment. Oops. A line segment. It's the exact same equation as a line. But t is in between 0 and 1. And this is going from the point z0 to z1. Okay. And this is also going from z0 to z1. A circle, the radius is r and the center is at z0. Okay, z0 is a complex number. So r of t, I denote those as position functions, right? Position vector functions. So it's z0 plus r times e to the it. Right, so that's a bit of review on some parametric curves we've seen in the previous chapters, right? So we want to look at how to parameterize a circle of radius 2, whose center is at 0, 0, the origin. And t is in between 0 and 2 pi, right? So the circle of radius 2, its parameterization, so I'll label this as z of t. This equals to, well, its center is 0, 0, so it's just, oh, it's the radius root 2. Excuse me. Oh, I'm sorry. Okay. I made a mistake, so this should be 4. Okay. I have in my notes that it's radius 2. So that, okay, yeah. Yeah, so 2. Okay. Circle radius 2, that's what I meant. All right. So it'll be 2 times e to the it. 0 to 2 pi. Okay. So this is z of t here. And okay, so if you see a line integral with a circle in the middle, that means you're dealing with a closed curve. So the circle is indeed a closed curve. It starts and ends at the same point. So this line integral equals to the integral from 0 to 2 pi of f of z. So this case, it will be 1 over 2 times e to the it times z prime of t, which in this case is 2i e to the it times dt. Okay. So e to the it's will cancel along with the 2's, right? And this will equal to the integral from 0 to 2 pi of I times dt. Which equals to 2 pi I. Okay, 2 pi I. All right. How about another example? Here's another one. Okay, yeah, it's right here. So shoot. It's 1 divided by z. C is the equals 1. Try to work on this for a bit. Okay, pause the video and try to see what you come up with as your solution. Okay. All right, I assumed you worked on this example. The best thing to do here is you want to draw out a picture to see what the contour looks like. So we're going to look at the right half of the unit circle. So they're referring to this contour right here. So so we're going to go this way, right? That would be the positive orientation. So 0, 1 here and 0, -1 there. Okay. So that's the contour they're referring to here. So what we need to do is figure out how to parameterize this contour. But that's easy, right? It's the so it's where z of t equals to e to the it, right? That's how you would define the unit circle. But t is going to be varied in between -π/2 and π/2. Okay. So yeah, so we're starting at the negative y-axis, right? The negative imaginary axis, and we're going counterclockwise. So yes, although this is 3π/2, it's also -π/2, right? Negative means you're going clockwise, so it's efficient to have the limits for t to be in between -π/2 and then π/2 radians. Okay, but and that's how you parameterize that contour. Okay, so this integral z plus 1 over z dz. Well, this equals to -π/2 to π/2 of so in this case e to the it plus 1 divided by e to the it times z prime of t. So that is I times e to the it dt. So this equals to minus I, the e to the its will cancel. So we'll have minus the integral from -π/2 to π/2 of e to the it plus 1 dt. And so this equals to I times 1 over I e to the it plus t. Okay. And so this equals to e to the it plus it. Okay. It's it. So cosine of π/2 is 0 and sine of π/2 is 1. Okay. Sine of π/2 is 1. So we'll have so the upper limit will be 1 plus π/2 times I minus, so that would be a -1 minus π/2 times I. Okay. So in this case, it's 2 plus pi times I. Okay. 2 plus pi times I. So hopefully that made sense. The last thing I want to talk about is different properties of complex line and properties of complex intervals. Okay. So the line integral of a constant times f of z dz is equal to k times the line integral of the function f. So k is a constant. Second. the line integral of a sum or a difference of two complex functions. This equals to the sum and the difference of the line integrals of the complex functions. G of z dz. Okay. If I have a closed piece, if I have a simple piecewise smooth curve, okay, C is a simple piecewise smooth curve. Okay, this would equal to the integral of C1 of f of z dz plus the integral of C2 of f of z dz. C1 and C2 are piecewise smooth curves. Piecewise smooth curves that are joined end to end. Okay. And the fourth property is if I have a line integral of a curve, f of z dz, this equals to minus the line integral of the function going clockwise. So minus c, this is referring to the curve going in the opposite direction. Of positive orientation, okay? So whenever you do that, you have to tack on a minus sign out front. So make sure that you take note of that, okay? And that's it for this section. So here's some problems for you to check comprehension. So page 218, 2, 4, 10, 12, 13, 15, 22, 24, 28, 30. Okay, when you have questions, please let me know. So in the next video, we'll look at one of the biggest fundamental theorems in complex analysis, the Cauchy-Groussat theorem. So thank you for watching. I'll see you in the next video.